All right, yes, good to go. It's taking too much time. So where was I last time? So I was trying to say something about convexity and the relationship with the SCR. So what did we prove last time?
Hessian is positive something told that.
So claim. So Hessian being PSD implies so I think I made a hash of defining. So this is nothing but it's always so the you can do this twice now. X1, F, and so on. So the ijth element, let me just define the ijth element of this, is nothing but d square by dx dou xij. That's okay. So this we showed. We would like the converse also to be true. That if the Hessian is positive semi-definite, then the function is convex. Is that actually true? We showed the Hessian was positive semi-definite, then the function was convex. That's a good test. If you wanted to test for a function to be convex, just go and check its Hessian. And we're done. Now we're saying, suppose f is convex. What can we say about the Hessian?
You have to check whether first the Hessian exists.
That is given. Of course, otherwise there is meaningless. So Hessian exists. It would be so nice if it was, if and only if. Just like our epigraph. With level sets, we got only one direction. So what do you think is going to happen? You have some, how did we prove this? Correct. So if you think of the same equation, whatever we did, if suppose the Hessian is positive semi-definite, what does it tell you about f? Because remember, in terms of the first order condition, we have if and only if condition. That if function is convex, then f of y is greater than or equal to f of x plus derivative of x times y minus x. And that is if and only if. And that's what we actually use to show this. Beside this being PSD, the third term essentially is positive, and then automatically tells us that f of y is greater than or equal to f of x plus derivative of f of x times y minus x. So this is greater than or equal to came because of the third term, which was nothing but what it was? X h z times. This should be a translation. And this quantity being greater than or equal to 0 gave us this. Now look at the function being convex. This equality still holds, right? But is that sufficient for us to claim that if f is convex, Hessian better be greater? It's clear, right? What we are trying to do? If this equation is sufficient, we should not look beyond it.
The equation can just tell us that there exists a certain Z such that is what? It might
That's okay.
no, in the sense that let's assume that it is convex.
Yes.
So we have that f of y is greater than or equal to f of x plus.
Yes.
It doesn't tell us anything about.
Okay. So now a little bit more, and then you can do it for every Z. So here, what did we do? We did the Taylor series approximation for a particular point that belongs to x comma y. Now, whatever your objection is, you could potentially remove that. And then you will possibly hit a roadblock. That's what I want you to think about. What is the usual Taylor series approximation?
One dimension.
Doesn't matter, one dimension. It won't hurt to think of it. What is the usual Taylor series approximation up to the second term? Sometimes you stop at the first term, sometimes you stop at the second term. So suppose you also want to include the second term. What is typically we do? What are we trying to say about Taylor series approximations? Point nearby. We don't go something like Z belonging to something. So if I were to do that so that I can remove this, what could you do? What would be the appropriate change of this equation? Your objection was that this was some special Z. But that can be removed. What do we do with usual Taylor series approximation? We say at a point x and nearby, this function is well approximated by something. You could just replace this with that. So what is the usual Taylor series approximation? Let's suppose you're interested in point x. What do you write f of x as?
Of A plus
A. Okay.
near A
We will fix A. Okay. Plus
plus F dash A
of A.
and of
Times?
A x minus
Okay.
plus
And plus what? This is not exact until I put in that the final term, right? Which is typically little o of, I'll tell you if you don't know what little o is in a second. Of what square? Essentially x square, but let's say it's minus x square. So O of f of x. So there are two notations, big O and capital O. The little o is essentially is equal to something such that, so this is equal to g of x. That is g of x divided by f of x as limit x goes to infinity. 0. So grows smaller than f of x. That's what it means by little o of f of x. So all these terms are only going to be smaller because we are interested in points around. So A belongs to the neighborhood of x. That's what it means. Okay, so suppose I had this. What can I do? I want to go from f being convex to saying something about the Hessian. What is the convexity of f tells me here?
Should be greater than equal to plus.
So there's something is actually wrong in this equation. Hopefully somebody will fix it. But beyond that, from our first derivative, if and only if condition, we know something. When f is convex. Sorry. Sorry? That's okay. That won't matter much. We will not come and haunt you. So just apply the condition that f is convex. You should get the first and the second term is greater than what? Something less than what?
And the first and second term are less than equal to Convex.
Okay.
So, but this thing is equal to Convex. The whole thing must be less than or equal to. No, the whole thing must be greater than or equal to.
You want something like that, right?
So the whole thing is greater than or equal to FOK plus delta FOK dotted with x minus a.
Okay.
And so we can remove that term. So we get that x minus a whole square, x minus a SCM time, x minus a transpose, that thing plus O of x minus a whole square is greater than
Okay. Now, can you identify a technical difficulty? No, little O, that's not. That will go to 0. So that's not a problem.
So if delta star should be positive.
That's okay, but that's not the problem. Problem is something else. Problem is in writing the Taylor series approximation. When am I allowed to do that?
you are only taking a small neighborhood around.
Yeah, but neighbor should exist.
Sorry,
Neighbor should exist, right? When does the neighborhood doesn't exist?
It's at the bottom.
So what kind of domain I can look at is the question.
Okay.
So I need this. So in general, that's not even true. That I don't have this equation if my domain is actually not open. So that's the technical difficulty. Rest of the proof is actually one line. So let's now do it properly. Okay. So the claim is the following. Phi be the domain as usual. FB convex over. Then if phi is open, then h of f is. That's what you want to prove. I would like to use chi always for my domain, but sometimes I keep using D just for that particular instance where D works better. So PSD is a standard acronym. It's not that I created it. Positive semi-definite. Okay.
even then, like, again, it's that I don't know if it's a trivial question, but even over there, like we're taking X minus this whole thing, Taylor expansion only holds for the neighborhood, right?
Yeah.
So we're proving that that thing is positive semi-definite only over that neighborhood, right?
No, but for every X. That's
Okay,
what.
right. But
That's why we'll plant an X here. So this is not precisely written. I will write something slightly different. Okay. So think of the point X, okay, and we'll take X plus some lambda D for D small. All right. Where does X plus lambda D belong? Being it open, I can always find small enough lambdas and D's such that this also belongs to. Okay. That's the important thing in essentially in any direction, whatever direction I want. So now I write a Taylor series around X plus lambda D, which is of X plus lambda D plus and lambda, remember the scale. Plus little of once you overcome the closed versus the open problem, then everything actually is trivial. Now, what does convexity tell me of F? That this thing is greater than or smaller than. So I want to compare this with these two terms added together. This is greater, right? We proved something last time. What was that something? F of y is greater than or equal to f of x plus the gradient at x times y minus x. So just plant y equal to x plus lambda d. Y minus x is nothing but lambda d. That's what is sitting over there. So taking y equal to x plus lambda d and applying first order condition for convexity, get that lambda square d transpose square hf of x d plus little o of lambda d square is greater than or equal to 0. Now what should I do? What I really want to prove is that this is positive semi-definite. And for that, I can essentially with or without a scalar, I can handle that. So I can simply divide this by lambda square and take the limit as lambda goes to 0. So divide by lambda square and limit. So we get lambda, sorry. D transpose. That's it. So as long as you handle that one small problem, that this domain should be open, rest is actually easy. So be careful. It's not if and only if condition universally. Convexity only implies PSD for the Hessian if the domain is open. You don't seem to be happy. Siddha, you don't seem to be happy. Something is wrong. Be comfortable. We're not in a hurry to go anywhere. At peace, we'll finish everything, whatever you want.
Why does this imply that holds for all D?
Or D. Yeah, whatever D I can take. Lambda small enough. That's why I need openness. See, D is a direction.
Okay, yeah, D is just like you can take lambda to be as small as you want.
That's the whole point. If this was not allowed, then so if I was not using that fat, I could work with closed sets. But I have to allow for all possible directions. So starting from X, I can go in any direction. I'm just scaling it down by as small a number as I like. Good. Always important to pinpoint why some technical condition is needed. So maybe I forgot to say this, but everything what we've been doing with convexity, if you replace the inequality with a strict inequality, you get a strictly convex. So rather than saying greater than equal to, if you strictly make it greater everywhere, those functions are called strictly convex. That's all. So here, now the interesting example is, suppose you had strict convexity. That is, this inequality here was between this and this was strict. Would you get a positive definite condition is the question. So compared to PSD, PD is simply that this is strictly greater than 0 for all. So can you think of a function where it's strictly convex, but the Hessian is not positive definite? That would refute what I'm asking. Otherwise, you'll have to prove. Proving is much harder. Is the question clear to everybody? What we're asking is, suppose the function was strictly convex, would you get the Hessian to be strictly, or rather positive definite, not positive semi-definite?
What if we do, for example, x squared itself?
Okay, what happens to x square?
We take this second derivative, we get 0.
Okay,
So
yeah,
it's strictly convex.
it is strictly convex.
Second derivative is 2. No, sorry, x. Oh, yeah, sorry, 2. Sorry.
So that doesn't work.
2.
But go further. X power 4. The next best choice is x power 4.
Right.
Now what happens? So whatever we're doing is actually correct. So look at x power 4. Now that has the second derivative 0 at 0, even though it's strictly convex. So you don't get strict, and you can go back home and see why it doesn't. Like, the proof will not work through. It's important to remember that. Okay. Okay, so now we have how many things to check convexity? So test number 1. No, definition, of course. So first principles. So that's the definition itself. What was the second thing we did? We did something with the level set. What was it? We did something with a epigraph. Fourth was first order condition. And now the fifth is the second order condition. You should be comfortable with all of them, because for a particular problem, which one you'll need, you never know. You can exhaust one by one, but that's terrible. Of course, these two work only if the function is differentiable. Okay, so now let's try to see some things we left behind in terms of examples. And we just believed for the moment that those were convex. For example, maybe the simplest was 1 by x. If you wanted to prove the convexity, which of the tests are the simplest? Yeah, second order is the easiest test. Everything else will require a lot of work, especially the first principle. Even the epigraph approach will take possibly a lot of work because to define it is a painful job. So second order condition is just, so what is the second derivative of 1 by x? First derivative of, so f is equal to, this is minus 1 by x square. Keep me honest, okay? Like possibly make a mistake. What, minus 2 or 1 by 2? 2 x cube with a plus. So this is greater than equal to 0 for all x greater than 0. That's what we are anyway interested in. Our domain was x greater than equal to 0. Okay. Did we leave behind any other function to say we'll check it later other than 1 by x? So we said something about f of x comma x times. This function we had at least a good idea why it was not convex. But now, can you directly show me that it's not convex? Use any test. You don't necessarily have to use anyone in particular. Which one do you think will be easiest here?
Last.
Okay. So,
It's 0, 1.
so that determinant is less than minus 1. So clearly it is not. But when do I actually get that? See, function being convex, the Hessian is positive semi-definite. The function being not positive semi-definite means what? Only if the domain. So that's what you have to worry about when you're doing something like this. So if domain is all of Rn or R2 here, it's actually not true. R2 is open. But if you constrain your domain to something closed, then you can't make the same claim. So to be very careful. You'll have to use some other test to claim. So that's why I wanted to bring this out very clearly, that only if the domain set is actually open, you can make this contrapositive conclusion. The positive test is easy. Function, the great Hessian being PSD, function is convex, you don't have to worry about things. The other way around, if you want to go, you have to be careful. You might want to say something easier is, let's say, look at the epigraph. There, you don't have to worry about all those things. So do worry about. So clearly the Hessian is not. Okay. What other functions do we leave behind? This definitely will left behind. We didn't say anything conclusively about it. Now, can you say something? So as long as things are differentiable, it's always easy to check the Hessian test.
Yeah, same determinant will be zero.
Sorry?
The determinant of the Hessian get is zero.
Okay, done.
No, we can still check some. Yeah.
What,
Okay.
what do we need to check?
Yeah.
For all xy, it is 0.
Yes.
No, no, 0 is, but is it 0? Okay, let's try to do it. So what will be the first term? Is simply 1 by y or 2 by y? Okay, this is minus 2 by y square. This is first x, right? So 2x by y square with a minus. And this is a symmetric, so it doesn't matter. Okay. Now,
That should be x square by y.
which one?
The last one.
Here.
2x square by y.
Oh, x square remains as it is. Sorry.
Right.
And this 2 should also with the plus. Yeah, sorry. So you get what? Then it's equal to 2 times x square by y power 4 with a minus and a plus. So 2 times 4x square by y power 4. What's going on?
Yeah.
This is also 4. Okay. Fine. What other function did we leave? Anything weird?
Look at an example, I don't know, something very strange maybe. What if we consider a harmonic function?
Okay, tell me.
So I only do because otherwise.
Okay.
Do like, so second derivative of x and second derivative of y, the sum of that is 0.
So tell me second derivative.
Go square x by dou x dx square plus dou square x by dou y square. That's 0.
Okay.
Like it has that property, right? Like at any point has
No, so in terms of Hessian, you're just saying that the main diagonal, the terms added together are 0. That's all you're saying.
yeah.
But that doesn't mean much, right? Because the cross diagonal could be one positive, other negative, depending on how the function is defined. So if both of them are positive, or even this is addition, the product is what will matter. So eventually, for a 2 by 2 function, this minus this. So the plus won't give you much information. So give me a function for which this is true, and then we can evaluate. But I don't think generically one can say much directly. Just given this condition, what you can say about the Hessian doesn't seem obvious to me.
In physics, we have that thing, right? Like that. A point like this is
No, I completely agree. Just that because the kind of test we're running, it's the additive part is not very useful here. It's not that it's unuseful, but if you give me one particular example, possibly it could be true. We can go ahead and evaluate. So x times y has this property.
Yeah.
Because individually it's 0. We'll have to think of other weird, like it essentially has to be a negative of each other. That's the only non-trivial case. If they're individually 0, it's not going to help. So give me a function for which this guy is negative of this y. Is there a simple enough function? What happens to minus x times? What should I do? What will happen here? So let's put x square also. Yes, this should work. So the first term is what? Minus remains minus because twice I'll take it. So it will just simply be 2y square. And this guy is simply minus x square times won't work. 2. So it'll be 2 times x square plus y square minus. Okay, it won't work.
X square minus y square.
To begin with, yeah, that will. But again, individually they're going to 0. That's the problem.
Usually
To x square, okay, sorry, yeah, that's correct. X square minus y square. So what is x square minus? It's a good function actually. It does show up quite often. Is it convex? Why not? What is the Hessian? The Hessian is simply 2 and 2 with a minus. What is this? You'll get 2x minus 2y. And it's the same thing.
you get 2x and
Sorry?
2x in the top line.
Here,
No,
this one.
yes.
So 2x,
In
right?
first derivative itself,
You
y
get
will be eliminated.
okay, that's right. That is correct. So similarly, you will not get here. So the determinant is minus 4. You're making some mistake somewhere.
The second that should be zero.
This one?
It should be symmetric. Zero.
Okay, so
And zero.
to
With respect to x, now this is with respect to like this is x.
okay, which one do you want to do first? First y? Okay, first y. So this is minus 2y, and then you take, it's just always easy to just do it rather than so determinant of score. So not PhD. So not convex. Looks appealingly looks convex, x square minus y square.
The shape is almost similar to x.
That's the point. But if you scale it up appropriately, you'll get all sorts of things. So ax square minus y square for different a's, you'll. That's still not. Right? So if I just scale up a, multiply a to x square, is there any value of a for which this is convex? No. It's always negative, no matter what you do. Good. Yeah, okay. It's a good function. Okay, what else are we missing, which we have discussed? Sorry. X over y. Yes, what happens to x? X square by y turned out to be PSD. What happens to x over y? That better not work. Yeah, so that doesn't work. It's strange, right? X by y doesn't work, x square by y works. So just by looking at the function, you can't make out unless you actually go ahead and do the test. Okay, so something which you're all familiar with. Geometric mean. Who wants to hazard a guess? Is it convex or concave or neither? So f of x is essentially a vector. It's product of xi, I going from 1 through n to the power. It's a weird function. So in 2 dimensions, what we have proved without the 1 by power of half, xy is not convex. Now suddenly xy to the power 1 by 2 seems to change its character. So you could first guess for n equal to 2 and then make a guess for arbitrary n. Did you try to write like geometrically see it's a convex or concave or nothing? Sorry.
I think the determinant in 2 dimensions is 0.
Good too. But what do you expect? What's the physical feel for the function? What does it look like in 2 dimensions? It's very important to at least be able to visualize.
The domain or the restrict the domain.
All positives. Strictly positive. Square roots. Square roots are involved, so everything is strictly positive. You want me to draw it? Let's try it. Let's say n equal to 2. And we are in positive plane over here. What will it look like around this point? It's clearly increasing, right? From 0 at least it increases. What happens to as
the axis is 0.
the x is 0? Why?
It's because one coordinate will be 0.
No. You want this way is 0. Okay. But anyway, I'm looking at everything above. I'm taking square root, so I can't even. So, okay, fine. Let's just stay away from it. Let's not even count 0. Okay. So what happens? This increases. That much is clear. Now what happens? This just keeps increasing all the time.
That's what I'm trying to increase.
Okay, so let's try to do this. Just for n equal to 2. This actually works. Whatever is going to work here is going to work for all n. So what is our? This is essentially d by dx1 of just writing in just to make sure that I don't make a mistake. All right. So what is this first term? Half times x1 to the minus half. Keep x2 aside and do one more time. So we get what? Minus 3 by 2. So 1 by 4 and a 3 by 2. Oh, so this will be similar here. Okay, what happens here? So x2 is half.
X2 the
Sorry.
X to the power.
Sorry, one guy.
The second term.
You're telling me this or you're telling me this?
No, the
Off diagonal.
The primary diagonal, the first diagonal.
Okay, what happened? X2. Sorry. Yes.
To go one by x. Raised to 1 by 2.
What happened now?
The new variable start. X2 and x1 raised to 1 by 2.
Yeah, in the primary diagonal itself, that thing is.
Okay, now this is half times x2 to the power minus half and another half x1 to the power minus half. And this is the same 1 by 4 x1 to the minus half. Okay, too many powers floating around. So what is the determinant? Sorry, these are minuses. Twice, right?
The past, the lower.
That's right.
Left, yes.
It's
Past
minus.
1 by 2.
Oof. That was a genuine type. I meant to write, others were mistakes. So now determinant of del square of f is equal to how much? 1 by 16. Make sure that I don't make a mistake now. This is a plus to the minus, so it will be x1 to the power half minus half. This is plus half adds to minus 3 by 2
Minus
So it's minus 1.
minus sorry minus 1, and similarly x2 to the power minus, and a minus again 1 by 16. Yeah. So in fact, this is 0. So what does it tell us? It's not convex. Or is it not convex? What is it? Convex, concave, what is? What can you? Why? Why not convex? 0 is fine, right?
Should be correct, but visually nothing will be.
So what's going on?
Should be above. Because closer to x and y axis, the values are lower than.
Yeah. So what is going? What's going wrong?
Point that all of them are equal, then we just be equal. Since all the coordinates are equal,
Mm-hmm.
at that point we have that when we just become equal to the arithmetic. So there it takes its maximum value.
Mm-hmm.
So as you were saying, I think it's correct. I don't know.
No, but why are you hesitating?
I'm not hesitating. I'm just like wondering as to whether it could be.
So what's wrong? That's the point.
It's increasing, but it's increasing under certain. We're taking the first part.
Sorry?
The first part. Only the first part.
Both plus. Both are strictly positive. Is determinant a good test for positive semi-definiteness?
Yeah, it's not necessary.
You need to check every determinant.
Not every determinant. Determinant is determinant.
Every vector we need.
As in, that for
So
determinant.
I was leading you on for a while, just checking the determinant less than, greater than. That doesn't actually mean that they are positive semi-definite. See, our condition was not the determinant of the Hessian was less than, greater than 0. The condition is the PSD. So what you actually have to check is whether it is positive semi-definite or not. So always keep me in check. I will keep tricking you all the time. So what you really need to check is whether this, once you have this, don't jump to taking the determinant. Multiply a vector and try to see what happens. So X transpose this, or no, sorry, let's call it Y transpose this times Y, and try to show what happens. Then you will get what you want, that it is less than equal to 0 for all possible Y.
Determinant test only works if we can check it's negative. Determinant is less than 0, then
Why?
even then it's not.
It's for one particular, see, what is determinant telling you? That one direction in which something is going to go wrong. So this means that the null space is not empty. That's all it is shown. But that doesn't mean anything about PSD.
Right, so we
For
can,
certain directions, it could be greater than 0. Nothing is wrong.
so we can use a determinant test to check that if we get a negative value, then there exists maybe no.
Why? Doesn't mean anything.
It's not clear.
So PSD is not equivalent to determinant being greater than or smaller than 0. It's very easy to fall for it, like we did today. So keep yourself slightly more firmly footed than you would like to be. So what you'll actually end up doing is you're writing that equation down, y times this times y, and use Cauchy-Schwarz. Convince yourself that that is in fact less than 0 and satisfies all the intuition you have that the function is actually like this. It's true, it's a concave function. So determinant is not a good substitute. That's the lesson we have learned for the day. Okay. So this is in fact trust they will go and check. So other functions which I'm not going to belabor the point. So log sum x, it's like overload. The function is f of x to be logarithm of the summation of exponentials. So x of x1 x of lots of overload. Is exponentials being added together, then logarithmic being taken from outside. What do you expect this function to be? If at all you would like to guess. See, logarithm as soon as you see, it's not going to be convex. That much is clear. So it's either concave or not concave also. That's the only possible choice you really have. Log from the outside is not going to allow you to have a function of convex function. That's not going to happen. It has a diminishing returns property. Now, with this, what would you expect? Again, you can take just two variables. See, with single variable, it's just x1. So that's both convex and concave. But with two variables, what happens? Log of x of x1. What do you expect this to happen? Well, leave this as an exercise. You'll see some surprise here. The exercise is not part of the homeworks. This is just I want you to go back home and get your hands dirty. And given that the assignment is due, you can do this after the assignment. It's up to you. But do look at it. These are important functions which you will possibly encounter in your research. Another important is log determinant. So f of x, so the logarithm of determinant of x. Now, what domain I should look at for x? Sorry,
N cross n matrix.
say it again.
N cross n matrix.
No, that is clear. But do I want to restrict? So I'm taking logarithm.
Yeah, like whatever it is called.
Yeah. So the domain chi is such that x, sorry, this is too many x's. X is, so this is the notation for PSD. I'm going to remove the equality. So positive definite. So set of all positive. So domain is it's a pretty bad notation. So determinant alone is not a nice function. We have seen that. Once you take log det over this domain, it's a concave function. There are many ways in which you can prove this. If you know what is known as entropy, this is entropy of something. And given that entropy itself is concave, this better be concave. That's another way of proving it. You can get your hands dirty by just knowing what determinant is. You can just directly work with determinant. See, determinant is the product of eigenvalues. And log of the product will essentially open up. So it's nothing but a summation of log of the eigenvalues. Now you have to start. Why should that work? We know that summation of eigenvalues is the trace, and trace was linear, so things were okay. Oh, so now let's go to so this is, even though we've done this before, this is slightly more important than just as it appears. So here I'm taking maximum point-wise maximum. So essentially, what will f of x be? For each x, I'm pulling out the larger of the two values. That's what my function really is. So this point-wise maximum really. You don't necessarily have to do this over a finite family. You can look at a class of functions fi. So let's call let's just call it family. Countable, uncountable, I don't care. Okay, now define f of x to be supremum over fi I belongs to. This will also have the same property as it. This is important for many reasons. You can use this. So if you're asked to prove something, a certain function is convex or concave, whatever, you can write whatever function given to you in terms of this and then say, because this is convex, that is also convex. And can somebody tell me why this is okay? Here, what did we do? We essentially looked at the intersection of the epigraphs because we're not being given anything about differentiability of f's. Why can I do that here when the family is not necessarily finite or countable?
The intersection will still be convex.
So that's all you have to notice, that I can do this over a uncountable family. But do notice that. You go from here to here. Tell me, how should I go? How did we prove this to be convex?
Using the epigraphs.
No, what exactly did we do with the epigraphs? What is the epigraph of f as a function of epigraph of f1 and epigraph of f2?
It's the intersection of the epigraphs of.
Correct. So now what will be the epigraph of f in the bottom case? So far we have not used the fact that family is countable, not countable. So what would be the epigraph of f in the bottom case? Just the intersection over an uncountable family I. What difference has changed?
Okay, I don't get it like this.
How did you do this when there was only f1 and f2? What is epigraph of f when f is maximum of f1 comma f2?
We looked at the epigraphs of F1 and F2 and took their intersection.
No, is it true that the epigraph of f is that, or we did
It
something?
is true, because F is defined to be the max.
Okay, so similarly, when I define it over a family indexed with I, what is the epigraph of f? What have I done from max to soup?
The domain where
I've not changed anything in the domain. If there are three functions on the top, f1, f2, f3, what would be the answer in terms of epigraph of f?
intersection of the three epigraphs,
4,
intersection of
5, 6, 7, I keep doing this. Bottom I've just written in family indexed by script I. So what is the epigraph of f?
intersection
Of what?
of epigraphs of having those index.
Yes. So now what do I need to show? That is true. Epigraph of f is definitely epigraph of that. Now to claim that f is in fact convex, what is the final step?
That the intersection should be convex of those.
Of the uncountable. The countable is clear.
Yes.
So that's all is needed. Like the intersection of countable intersection is convex, you just have to show that uncountable intersection. So always remember where is the pin pressure point. You can always write epigraph of f as the intersection of I script I, epi of fi. So far there is no trouble. All you have to show that this is also, if each of these are convex, this is also convex. That is the question which I'm not going to. That's all. So before we go on to the final important thing, look at this function. So x again is a vector. Summation. So x1 minus x2 plus x2 minus x3. Let's just take 4 dimensions. Erase this. And x is x1, x2, x3. What kind of function is this? And you can safely assume what doesn't really, it's not important. All xi, let's say greater, doesn't matter. Now differentiability is gone, so this is no longer first order, second order. If you want to think about it, you can even think about it in 2 dimensions, no problem. Just mod of x1 minus x2. So each vector is x1 comma x2. Function value is mod of x1 minus x2. What kind of function is this? Okay. What about 4 dimensions? When it's not seen, just stare at it for a while for the 2 dimensions. Once you're convinced, then go to the 4.
That is one. It is less than or equal to that.
Okay. And how did you convince yourself?
Like, I mean, you can prove that like if you take lambda equal to half, and then you just prove that f of x plus y by 2 is less than or equal to f of x plus f of y by 2.
That's enough.
Yeah.
But that's a special lambda, right? It should hold for all lambdas materially.
But then, yeah, one dimension holds for all. Like, it holds for half and holds for all. You can, we have to like, you can use a triangular inequality, even if you use lambda itself. You just have to use a triangular inequality to still follow.
No, I'm not saying that it's not possible.
Sum of convex functions.
Mm-hmm. Is convex, that we know.
Yes, and x1 and x2 is convex.
except you have to be little worried, right? Because when you're talking about convex functions here, they're in lower dimension. Because what is f is given in 4 dimensions, but each one of them is living in a 2-dimensional space, right?
We can define x x1 x4 as the
Correct.
mod of x1 minus x2.
Yes.
So it is still a 4-dimensional.
Okay. And now what do you want to do?
Just 2 inputs.
Yeah.
So,
Okay.
Sum of.
So sum of convex. So all you have to establish was it's convex in 2 dimensions. There are, and what the function looks very interesting. What does it look like? It's 0 on this 45-degree line. So my 3D skills, let's see how bad they are. So in this line, it is 0. So, and then it just increases. So it's increases like this. And how do I draw this? This is how it will, essentially with the similar slope around 0. So slope will be symmetric around 0. That's how it will be. So if it's, laptop, you open it up, that's what it looks like. On the meeting point, it is 0, and it's opening up like a book. This book open. So this is, and then you add it up, you'll get whatever you want to get. Now let's play a trick. Okay. So this is f of x. Let me do first g of x. G of x, all it does is it permutes elements of x in an increasing or non-decreasing order. What does it mean? That the output of this, so this is x. So G is Rn to Rn, where it takes the output is essentially, I'm being sloppy here, so x1 tilde less than x2 tilde. Just a permutation where whatever input was given to me, I just permute in such a way that they're in increasing order. And now apply f. Is the function clear?
F of g.
Yeah. So f of g is what the final function is. First you do, so you take a raw vector, permute its coordinate in such a way that the first coordinate is smallest, second coordinate is the second smallest, and so on. And then apply this. Do you think anything will change here? Sorry? Yeah, 2D, nothing changes. Because they're symmetric. 3 and 4, something will change. Some like functions of this type which look intimidating. How did we actually get rid of the intimidation? Is to look at sub functions and then this collapse. So we learned lots of things, max of something, addition of things, this, that, g, f of g, g of f, whatever. So now, what is this g of f did we learn? If you remember, f of g of doesn't matter which order.
It is convex and that is continuous.
Not decreasing. So these have to be convex, and then the outer one or the inner one? Outer one. Okay. Now increasing has to be very carefully defined. It's a vector. So you have to order them and blah, blah, blah. So whenever you're encountering things, recall everything that you're possibly done.
x4 minus x1.
What?
Essentially, not the order, we can just remove the magnitudes, right?
You can remove the magnitude, but x1 minus x2, right? So x1 is the smallest. So how can we get, it's still negative is possible. x2 is possibly larger than x1.
But the final value, the f of g, you know that x2 is bigger than x1.
Correct.
So mod of x1 minus x2 is just x2 minus x.
You can reverse it, that is okay, but it's not x1 minus x2, it's just x2 minus x1. Fine.
Is x4 minus x.
Correct. So now after you add it up, what do you get? See, something strange is happening here, if you notice. Because I've ordered them in a certain way, the mods will essentially I can get rid of the mods. That's the whole point. And then such a sum without the mods is nothing but the last term and the first term, depending on whatever sign you got. So is it convex? It has become linear. So it's convex. So I constructed a very complicated function and eventually it turned out to be something very simple. So don't get intimidated by the way it is written. Half the battle is won in convex optimization by rewriting functions. A certain way you'll see, I've not defined yet the following thing. A problem is convex or not. Because why we care so much about if the problem is convex or not? Because there are solvers available which can take any input as a convex and spit out the answer. The problem is non-convex is the hard part. That doesn't look like what we will define a problem to be convex problem. All the game is in rewriting the problem in terms of the constraints or in terms of the objective. I've done nothing of this sort. I'm saying rewriting is a big part of your arsenal, what you will carry through. Rewriting a problem, rewriting constraints. How do you want to write the same constraints in many different ways? Some of them will make it very easy for you to look. Some of them will make it very difficult for you to see. So that's why if you see such functions, try to find the ways in which you can get rid of them and write something very simple. Okay, so
Last one.
sorry.
So we're computing them in increasing order for each point, right?
Yeah.
So, but then for each point, if you're doing it for each point, then why should it be xn minus like?
No, so take any x. Once I do this, then I input this to this. This looks at in the particular order. What is that order? It's an increasing order.
Yeah.
So it's not necessarily the fourth element given to you, but some two elements picked up from here. Those difference will show up here.
Okay.
So it's not necessarily the fourth element here.
In that, this is the
But from the original point, but it's two coordinates picked up and some negation happening between them, which is linear. So I don't have to. So it's not necessarily the fourth coordinate of the raw element. So I'll prove it next time, but this is something very important. So like we said something about convex sets, right? What was the final characterization we give for convex sets? They're essentially the intersection of all the hyperplanes that contain them. Something very similar for convex functions. Okay. So let F be Rn to R. So this point is important that it's all of Rn. Otherwise, you need some technical conditions. And F is convex. Then something strange happens. Then f of x is nothing but supremum over all functions g of x, where g is affine and gz is less than or equal to fz for something very strong. Just parse it for yourself. What are affine functions? Essentially ax plus b, those kind of functions. So any convex function, remember, it could be arbitrary. It's not asking you to find them. All he's saying is there exists affine. So every f of x can be written as this. So that is point wise. So for each x, see, it could be different g's for different x. Okay, that this holds. See, too much to ask for the same g to work. But still something highly non-trivial. So just pay attention to this, write it down in your notebook, go home and you can at least try to show one direction less than equal to or greater than equal to. One direction is harder, other direction is easy. One direction should be just automatic. That f of x is either less than or greater than, that should come trivially. The other part is what requires a proof. Because of this, one direction should be trivial. Because I'm looking at all g's for which this is true. So one direction is kind of trivial. The reverse direction is what all the work is required. So let's stop here. You can take your time, write it down.